Hello Year 11, this is the Combined Science Physics Higher Paper 2 Masterclass. Make sure you're watching the right video or you're in the right room or you might miss something that's specific to your tier. Okay, so jumping right in, make sure for this exam that you have a protractor, a ruler, a scientific calculator. Okay, lots of people will forget the protractor in paper 2, so make sure you remember to bring it. Okay, so just like the last one, this is going to be split into two different types of sections. We're going to have red slides where you're listening, you're reading, you're finding mistakes, and you're listening is the key part. And green slides where we're reflecting, we're writing, and we're fixing mistakes. The only thing you're going to need is a pen and a piece of paper or a whiteboard, something that you can jot some information down on. Okay, so first things first, we want to look at the required practicals. Now this required practical is about Newton's second law. It's about how force, mass and acceleration are all linked together. Now I think this is one of the more challenging required practicals in the paper 2, and I also think there's a good chance that this one will come up. Okay, now we've got two different setups here. We've got a trolley with some marked lines, we've got a pulley and a weight hanger, and a slightly different setup where we've got a glider on a vacuum cleaner that's blowing air up underneath it to reduce friction. We've got light gates, and again we've got a pulley and a weight stack. So what I'd like you to do first, I'd like you to think about first, how is this an improvement? What does it change? And what do I use each piece of equipment for? What's the job of each bit of equipment? Okay, so I'm going to pause the video here and think about what is that big improvement and what do I use each piece of equipment for? Okay, moving on. So one of the things that I think is key in all your required practicals is you want to really be careful of your language and say what piece of equipment you're using and what you're measuring. So things like here, we've got these lines, okay, we're allowing these lines to help us measure acceleration. Okay, they don't measure it directly, but they allow us to calculate it. So what happens is we let the trolley go and the trolley passes through these lines, and we can use a stopwatch to record the time it takes for them to pass each line, and we can use that information to calculate speed. Speed is distance divided by time. And then we can look at how that speed changes as the trolley moves down the table. Okay, and that allows us to get our acceleration, because our change in velocity divided by the time it takes will get us our acceleration. So it's quite difficult to write that down in a way that makes sense, but make sure that when you're writing your method answers that you state what you're measuring and what pieces of equipment you're using to measure it. That's key. Okay. Now the big improvement from this setup into using light gates is that light gates don't depend on human reaction time. If we're using a stopwatch to measure the time it takes for the trolley to move past these lines, then it will be affected by reaction time. Okay, so light gates eliminate that. The principle is pretty much the same, however, that this interrupt card will block the path of the light, which allows you to work out the speed at the first light gate and then at the second light gate, which allows you to calculate the acceleration. Now there's lots of different ways you can set this practical up, lots of different ways. Okay, there's different ways you can measure the acceleration, so you could use these two methods. You could also use ticker tape. You can change the way the force is varied. So you could use a spring system that you would compress a spring a certain distance, which would allow you to control the force exerted on the trolleys. Or you could tilt the table up at different angles, which will allow you to control the force acting on the trolley down the ramp. Okay, there's lots of different variables that you could change. Okay. Now, in terms of the results, okay, you also need to know how force and acceleration are linked together and how mass and acceleration are linked together. So your next job, I'd like you to try and sketch the two graphs and describe what they show. What is the relationship between force and acceleration? What is the relationship between mass and acceleration? Pause the video here and give it a go. Okay, moving on. We've got acceleration and force. We have a straight line that goes through the origin. That means that acceleration and force are directly proportional. Okay, with mass, as the mass increases, the acceleration decreases. Okay, it's a curved line. This means that it is inversely proportional to mass. Okay, so force and acceleration are directly proportional, mass and acceleration are inversely proportional. Okay, and that is the evidence that we need to show that Newton's second law is true. force equals mass times acceleration. Okay? Right, moving on to our next practical, we've got investigating Hooke's law, looking at springs. Now, one of the things that's really commonly mistaken is the difference between length and extension. Length is not extension. They are different things entirely. Okay, so the first thing I'd like you to try and do, I'd like you to pause the video and write down how could you accurately measure the extension of this spring. Pause the video now. Okay, moving on. There's lots of different ways you can measure that extension, but the key thing is you need to know the original length of the spring. Okay, because extension is the final length subtracting the original length. It's the difference between your original and what it's been deformed to. It's not just how long the spring is once it's been stretched. Okay, so you'll need some method of measuring the original length and the final length. Okay, now a really good way of doing that is by attaching some kind of pointer onto our spring that points at our ruler, our scale, and allows you to accurately measure where it is. That will improve your result rather than just holding up a ruler next to the spring. Okay, but that key part, the extension is length, take away length. Final length, take away original length. Okay, right, moving on. What will the graph look like? We've got force and extension. Be careful, we've got force on the y-axis in this case and extension along the x-axis. What will the graph look like? Include in your sketch the point of the limit of proportionality. Describe the relationship between force and extension. How would your graph change if the spring was a stiffer spring or a weaker spring? Okay, so pause the video here. Okay, moving on. So, first thing, I just want to point out some difficult language. The fiduciary marker, this is just a fancy science word for a pointer. Okay, that's just your needle that's attached to your spring. Okay, but our graph looks like this. With the first region, where we've got low forces, that's linear. This is where Hooke's law is obeyed. Okay, as we increase the force, the pattern stops being a straight line, it stops being linear and starts to curve. And at that point, we call that the limit of proportionality. And past it, it's non-linear, it's curvy. Okay? When we're in this linear region, this straight line section where Hooke's law is obeyed, if we were to release the force, the extension would decrease and would go back to its original size. Past the limit of proportionality, once we release the force, the spring will be permanently deformed. Now, one thing you've got to be really careful of when we're looking at Hooke's law is the graphs. When you're looking at the graphs, be very careful of the axes, because unlike most of the other practicals, you do get both variations where you can have force on the y-axis or extension on the y-axis. Now, generally speaking, we put force on the y-axis and extension on the x-axis to make it easier to calculate spring constant. Because all we need to do is look at the change in the force, so how far up the y-axis it goes, divided by the change in the extension, how long the x-axis it goes. Okay? And it's easy to do if we have force on the y-axis to do that. But because in our experiment, the thing that we're changing on purpose, the thing that is the independent variable, is the load, the force acting on the spring, a lot of the time that will be put on the x-axis, just by convention. Okay, so be really careful when it comes to any questions about springs that you're observing what is on the graph. Okay, the other thing that can be tricky about this is it does link with paper 1 content. You can be asked about an energy content, an energy store within the spring, and if you're asked to do that, remember to use the equation sheet to use that calculation, but also know that the area underneath the graph is the energy stored within the spring. Okay? Right, moving on to the next practical. We have infrared. Okay, now we've got this Leslie cube here. We'll fill it up with hot water, and we've got 4 different types of surfaces, and we've got an infrared detector that will measure how much infrared radiation is given out. Your job, I want you to try and sketch the bar chart. What will that intensity look like for the different surfaces? Pause the video here. Okay, moving on. So The most important thing you should note is that matte black has the highest infrared intensity. Matte black will give out the most infrared radiation depending on these colours. The worst, the poorest emitter of infrared radiation will be shiny silver. Okay, shiny silver. Shiny black will give out more than matte white and shiny silver, but not as much as matte black. Now, matte, when we're talking about the colours of surface, just means it's not shiny. Okay. Now, there's lots of different ways of doing this experiment. If we don't have access to a Leslie cube and an infrared detector, we can just use different coloured cans. And this is the experiment that you will have done. We'll have filled in some water, same volume in each can of hot water. We'll have 3 different or 4 different or 5 different surfaces, and we'll measure the temperature. Okay, we'll measure the temperature. Okay, so think about, what would you do? Can you write down a quick method to figure out which of these cans, which of these surfaces will emit the most infrared radiation? How would you present your results? Would you present it in a bar chart or something different? What will you measure? Think about all the different pieces of equipment. Okay, so pause the video here and see what you can do. Okay, moving on. So here's my pretty simple method. We're setting up as shown in a diagram. We fill the metal cans with the same volume of hot water, 200 millilitres. We make sure that each metal can starts from that same initial temperature. We record the starting temperature and then measure the temperature at regular intervals at every 30 seconds. Okay, or you could do it for a minute. And we record that temperature change for 10 minutes. Okay, now the big risk in this experiment is the hazard is that there's hot water. The hazard is the thing that is dangerous. That can cause, this is the thing that it can harm, how it harms us is the risk. Hot water can cause burns, and we reduce the chance of that happening by not overfilling the kettle, carrying the experiment while standing up, and wiping away spills and things like that. Okay, so presenting the data, okay, I would use a XY graph. I would use a scatter graph or a curve. Okay, I wouldn't use a bar chart. You might use a bar chart if you just measure the end and the start temperature, but I think it's better, especially if we're taking all these results, to just show that cooling curve. Okay, and what I'd like you to do now, I'd like you to pause the video and write down which is the best emitter and which is the worst emitter, and how do you know? Okay, moving on. So, the black can cools the fastest. That tells me it's the best emitter of infrared radiation because it is giving out more infrared radiation than it's absorbing, so it's losing energy, so its temperature decreases. And because it's decreasing the fastest, that means it's losing the energy the fastest, so it is the best emitter of infrared radiation. Silver is the opposite. Okay, it's still decreasing in temperature, but not as rapidly. Okay, it's not giving out as much infrared radiation in a second as the black. That means it's not losing as much energy, so its temperature remains higher for longer. Okay. A different way we can look at this experiment is by looking at absorption. Okay. We can look at a heater in the centre here, and we have 2 different surfaces. We've got a shiny surface and a matte black surface, and we have a weight that's stuck onto the surface with some candle wax. Okay. What do you think is going to happen when that heater is turned on? It's going to emit infrared radiation, and it will absorb that radiation on these surfaces. Okay. And I want you to think about these following questions. What surface is best at reflecting heat energy? Which surface is best at absorbing the heat energy? Why should the plates be the same distance from the heater? Okay, I want you to think about those 3 questions. Okay, pause the video here. Okay, so because the matte black weight fell off first, that tells me it's going to absorb more infrared radiation than is reflecting. So the matte black surface is better at absorbing infrared radiation and not very good at reflecting it. Whereas the shiny surface is much better at reflecting the infrared radiation than it is at absorbing. If the plates weren't at the same distance, okay, you wouldn't have the same amount of infrared radiation hitting the 2 surfaces. So it wouldn't be a fair test. That distance between the heater and the surface is going to be your most important control variable. Okay? Right, next we have different things. We have scalars and vectors. One only has size or magnitude. Magnitude is just a fancy word for size. And the other, vectors, has magnitude and direction. Okay, I'd like you to jot down a list of scalars and vectors. Give it a pause and give it a go now. Okay, so here is a list. We've got distance, speed, temperature, pressure, time, energy, power. All of these quantities do not need a direction. Okay, it doesn't make sense to say that the cup of tea was 80 degrees Celsius to the right. Okay, these don't have direction. They've only got an amount. They've only got a size. They've only got a magnitude. Whereas the vectors, these do need a direction. It matters which way you push on something. Okay, you can accelerate north. Okay, these will have directions. Okay, right, next job, I'd like you to try and describe what's happening in each graph. What is the motion of A, B, C, D, E and F? Okay, what's happening in each graph? Pause the video here. Okay, so in the first instance, first graph, the motion is stopped, it's stationary. The distance is not increasing and the distance isn't decreasing. It's not changing distance, the thing is not moving, it's stopped. Second graph, we're moving at a constant speed. Every bit of time, we're moving by the same bit of distance. Okay, we've got a straight line that tells us it's a constant speed. Third graph, this is a constant speed, but the distance is decreasing. So we will be returning to the start, the origin of the journey. Okay, it's a straight line, so it's constant speed, but it's got a negative gradient, so it's going backwards. Here we've got accelerating. It's not a straight line. Okay, and at the beginning, we're not moving very fast because the gradient is quite low, quite flat. So we're moving very slowly at the beginning, and we're getting faster and faster and faster and faster until we get to the end where it's going pretty fast. So this shows acceleration. The velocity is increasing. Here we've got decelerating or deceleration. We start moving quite rapidly, and as time goes on, the gradient becomes flatter and flatter and flatter until we're almost stopped towards the end. The last graph shows we're moving at a constant speed because it's a straight line, but it is moving slower than this graph B. We know it's moving slower because the gradient is much lower. Okay, right, moving on. I'd like you to do the same thing, but it's different. Be very, very careful. It's really common to mix up these two different types of graph. Notice that these are no longer distances. This is now velocity, and each answer is different. Okay, so again, I'd like you to pause the video and write down what is the motion in each case. Okay, moving on. So in the first case, we've got a constant velocity. We've got a straight line, which tells me the velocity is constant, and it's flat. It's not increasing or decreasing. Okay, so it's not accelerating. It is not stopped. Stopped would have to be at the bottom at 0. So this is a constant velocity. It's a really common mistake is to mix up this graph with the distance time graph and write that it stopped. It is not. Look at what's happening to the velocity with time. Look at it. Is it increasing or is it decreasing? If the velocity isn't going up and the velocity isn't going down, it must be moving at a constant velocity. Okay? This next one shows acceleration. The velocity is increasing as time goes on. It's getting bigger and bigger and bigger. And it's accelerating at a constant rate because it is a straight line. The next graph, this is deceleration. The velocity is reducing with time, and it's at a constant rate because it's a straight line. Here we've got increasing acceleration. We start off with a relatively low velocity, and as we're going up in time, the velocity is increasing, so it's accelerating. But because it's a curve, we know it's not a constant rate. Okay, the acceleration is getting bigger and bigger and bigger and bigger as we're going on in time. Here we've got decreasing acceleration. This one is incredibly important, and it links to our next slide on terminal velocity. Okay, we start with a relatively low velocity, and the velocity increases, so we know it's accelerating. but it does so with a smaller change every bit of time until eventually we get to a point where it's almost constant velocity. The last graph shows that something is accelerating because the velocity is increasing, but it's at a lower rate than b. It's not accelerating as much as b because the gradient isn't as steep. Okay, moving on. Next we've got the terminal velocity. We've got to try and describe what's happening in terms of forces and how is that affecting the acceleration of a parachutist. So you need to describe what's happening. Try and annotate this sketch graph. Okay, pause the video here. Okay, moving on. The key part about terminal velocity is that a drag force is involved that isn't constant. The drag force is affected by the speed of the thing, in this case the parachutist, and their surface area. Okay, so at the beginning, just as they're jumping out of the plane, when they're not falling yet, their speed is 0, the drag force is 0. So the only force acting just as they're exiting the plane will be their weight, which causes them to accelerate. As that person accelerates, they get faster, which means that particles in the air are bumping into them, which means that air resistance will start to reduce their resultant force. Okay, here we've got the force diagram shown. So at this position B, weight is still bigger than air resistance, okay, but not by much. But if weight is bigger, we're still going to be accelerating, so the speed keeps on going up. It's only at this point that the weight and the air resistance are equal, where there's no resultant force, and if there's no resultant force, then it will stop accelerating and it will move at a constant velocity. This is what we call terminal velocity. Then when the parachute's opened, it has a really large surface area, it will increase the drag force, okay, which will cause the parachutists to decelerate. They'll slow down, okay, until they reach a lower speed at which the weight and the drag force are equal again. And we'll have a new, much slower terminal velocity, making it safer to land. Okay? Right, moving on. Laws of motion. I'd like you to try and read the laws of motion and fill in the missing words. Pause the video here. Okay, so first law. If the resultant force on an object is 0, then the object will stay stopped or continue to move at a constant velocity. The second law, force is mass times acceleration. If the resultant force acting on an object is increased, then the acceleration will increase. Okay, if the mass on an object is lower, then the acceleration will increase. Okay, so if you have a bigger force, you'll have a bigger acceleration. If you have a bigger mass, you'll have a smaller acceleration. The third law, according to Newton's third law of motion, whenever two objects interact, they exert equal and opposite forces on each other. Forces come in pairs. So here you've got an example of a force interaction pair where we've got a satellite orbiting the Earth and they are attracted to each other. Okay, the gravitational force of attraction. Okay, now sometimes it's difficult to see where the pair is, but it is always there. That forces always come in twos. Right, moving on, some exam questions. I'd like to try and spot and fix the mistakes. Pause the video here, see where the student has gone wrong. Okay, moving on. This is a really common mistake, this first one. We've got balanced forces, the resultant force is 0. That does not mean the man is stopped. Okay, balanced forces mean it's not accelerating. It's not that it's stopped, it's just not accelerating. Okay, and this last one, when force A increases, the man will start to move forwards. There will now be a resultant force. Because force B is in the opposite direction of force A, it will be unaffected and stay in the direction to the right. It's not really getting any marking points. Okay, this student got confused by the first bit, which stopped them being able to get the marks for the second part. Okay, this question's really about terminal velocity. Okay, so we need to describe the movement of the man. They're moving at a constant velocity. They're not going to accelerate. They're not going to decelerate. They're not going to get faster. They're not going to get slower because the force is 0. When force A increases, we need to start explaining what happens to force B and to the movement. So you're going to get marks for what happens to force B and explaining it. and what happened to the movement and explaining it. So the man will accelerate. This causes force B to increase, okay, until it equals force A. The man will move at a higher constant velocity, okay. They reach terminal velocity. Terminal velocity Terminal velocity is not always a parachute and a skydiver. It's anything where an object is moving through some sort of fluid, so a gas or a liquid, where the drag force will increase with speed. Okay, so you could have a ball bearing and some thick liquid like soap, and you could drop the ball bearing through and you could measure the distances. And as soon as you notice that distance 5 is the same length as distance 6, that must mean, if we're recording these for the same given amount of time, that must mean that it's reached terminal velocity. Okay? Right, next, velocity time graph. Okay, another little question. If we've got velocity time graphs, we need to know that the area underneath a velocity time graph is equal to the distance. Okay, now what you're going to have to be able to do is split your velocity time graph into triangles and into rectangles and squares. Okay, you can work out the individual area of each of those parts and then add them up to get the total distance travelled. So I'd like you to try and find the total distance travelled in this journey. Okay, pause the video here. Okay, moving on. So this one's a little tricky to maybe get all of the triangles and rectangles. There's a number of ways you can do it. Okay, but this is one example of how you would do it. And the total should be 2,175 metres. Okay, now remember, you don't get given this. The area of a triangle is half the base times by the height. Okay, right, next question. What on a momentum? Image shows two ice hockey players. They're moving towards each other before a collision and then they collide. During the collision, the total momentum is conserved, and here we've got our answer about what is conservation of momentum, and it says momentum does not run out. And then we've got this calculation. Okay, now remember in your exam, you're given the equation sheet. It is double-sided. Okay, use the right equation. This is the correct equation. Okay, pause the video and see what you can do. How many marks will you get? Okay, moving on. So we don't get any marks for the first question. We do get a mark for one part of our substitution where we're working out the momentum of player A. We get 1 mark for this, but we lose everything else. And the important thing is vector is a direction. It is a vector, momentum is a vector, and the direction matters. It matters which way the velocity is going in. So we need to be really careful of these negative signs. Okay? So in terms of what is conservation momentum, the total momentum before will equal the total momentum after an event, be that a collision or an explosion. Okay? Here I find it easier to work out the momentum of the individual players and then find the total momentum. And once we've got the total momentum, we'll be able to calculate the velocity of the two players after they're squished together. Now you're only going to get asked questions about explosions where the total momentum at the start is 0, or collisions where you've got some total momentum. Okay, so be careful of those. Next, I want you to fix the mistake. Okay, we've got a magnet system, we've got a wire, and we need to figure out what direction the force is acting in, what effect this is, and we need to explain why the force acts on the wire when the switch is closed. So pause the video here and find the mistakes. Okay, we're not getting any. So it's not the magnet effect. Okay, the force is in the wrong direction, and we're not getting any marks for this ring. The wire is placed between the opposite poles of the magnet. Because the wire is made of metal, it will be attracted to the north pole of the magnet. This attraction force is the act force. This is not enough to get any marks at all. Okay, the metal won't be attracted to the magnet, most likely because it's copper for one. Okay, so we're not getting any marks for this. What we need to say is it is the motor effect. Okay, it is the motor effect. Anything that causes something to move when there's a force produced by magnets, you're going to be thinking about motor effect. Okay, and in terms of the explanation is nearly always the same. When the switch is closed, current flows in the wire. So the first thing you need to be aware of is current is flowing in the wire. And in this case, it's flowing from the positive end, the large bit of the battery, through to the negative end. Okay, so current flows through the wire, which induces a magnetic field around the wire. This interacts with the permanent magnetic field, which will create a force. Lots of questions will ask you, describe the motor effect, and they won't talk about that there's a force generated at the end, and that'll be the last marking point. Okay? Now, in terms of the direction, we need to use the left-hand rule. Okay? And in this case, we need to know that the battery, the large side, is the positive terminal, so our current is flowing from X towards Y. Okay? So we need to point our second finger along that direction. We're pointing from X towards Y. The field goes from north towards south. So that's going into the screen. Okay, so you should be pointing your current finger, your second finger, from the X to the Y, so from the left to the right. And you should be pointing your first finger, the field finger, into the screen, which means your thumb is pointing up, and the thumb is the force, and that's where we need to draw the arrow. Okay, make sure you use your left hand. Okay, if this question comes up, if a left hand rule question comes up, there'll be lots of people around the room who are going to be putting their hands up in the air, moving the paper around. And remember, you can turn the paper on your desk, so you can turn your page upside down, which might allow you to hold your hand a little bit more comfortably. Okay, but there's going to be at least one or two of you who use your right hand by accident. Don't. Use your left hand. It's Fleming's left hand rule. Okay? Right, next. You need to know the electromagnetic spectrum. Okay? I'd imagine most of you are able to sing the song about the order. So what I'd like you to try and do, I'd like you to put them in order of wavelength from long wavelength to short. I'd like you to give a danger and a use for each part of the EM spectrum. Pause the video here and give it a go. Okay, moving on. So we've got radio waves, microwaves, infrared radiation, visible light, ultraviolet, X-ray and gamma rays. Now the radio waves have a long wavelength and they have a low frequency. The gamma rays have a short wavelength and a high frequency. Okay? The higher the energy, generally speaking, the more dangerous. So gamma rays, X-rays and ultraviolet, these are all ionizing types of radiation. Okay, electromagnetic radiation, all ionizing. That means they can cause cancer. Okay, not very nice. In terms of uses, I've got a big table of uses here. So things like radio will be used for television, radio broadcasting, satellites. And we've got all these different uses here. I'm not going to read them all out. Okay. In terms of the dangers, lots of people they're not quite specific enough in terms of the danger of microwave and infrared. Microwaves can cause internal tissue burns because the microwaves can penetrate into the tissue of people. Whereas infrared will cause surface burns. They'll cause skin burns. Okay. Now, that's my last slide. I hope that was useful. I wish you the very best of luck. You're nearly there. Almost finished all your GCSEs. I'm sure you can absolutely smash it. Remember to bring a calculator. Remember to bring a ruler, a pencil, a pen, and a protractor. Okay? The very best of luck. Good luck, Year 11. Take care. Bye-bye.